Hello, welcome to another module in this massive open online course. At today's module, let us start our discussion, or let us start looking at another very important concept or property of a matrix, that is known as the rank of a matrix. Alright, so we were going to, let us start our discussion on another very important aspect, which is the rank, right? Rank of a matrix. Okay. So, in order to and this is a very important concept, this concept or this notion of rank is a very important concept, it is one of the fundamental properties. So, let us to start this discussion, let us again begin with an M cross N matrix. Alright, I hope all of you remember we have this M cross N matrix A11, A12, A1N, A21, A22, A2N, AM1, AM2, AMN, and this is your A1 bar and this is your A2 bar. Let us call these, each of these columns, remember we can represent a matrix as a collection of n columns, right. Each column is basically of a vector of size m, where m is the number of rows. Alright, so each of these, so m columns, so these are n columns of size m. Okay, so these are n columns of size m, or basically n columns, each you can think of these are column vectors of size m cross 1. Okay. Now, we define this notion of what is known as the column space, which is essentially y bar equal to Ax bar, which is A1 bar, A2 bar, An bar. This is your matrix A. Remember, you can think of that as the matrix A multiplied by this vector n x bar, which now performs essentially a linear combination of the columns of A. So, the matrix multiplication with a vector x bar, you can view it as nothing but a linear combination of the columns of A. So, x1 A bar, A1 bar, x2 A2 bar. So, this is basically nothing but, you can see this is essentially a linear combination. We have already seen this concept of linear combination. This is a linear combination of columns of A, and we call this vector y bar, which is a linear combination of columns of A, as belonging to the column space. That is, we say this belongs to the column space of A. Alright, so this C of A, this is essentially the column space, right. This is essentially the column space of A. What do you mean the column space of A? This is a subspace. So, C of A, this is the column space of A, this is the subspace spanned this is the subspace spanned by columns of A. That is essentially, if you look at it, this contains, that is, if you look at the column space of A, what do you mean by columns of A contains all possible linear combinations of the columns of A. Okay. So, that is it contains all contains all possible linear combinations of columns of A, all right, all possible. So, now we come to another important concept, right. So, this contains all that is subspace spanned of the columns of A. Now, we come to another important concept, that is linear independence. Okay. So, linear independence. What is linear independence? Now, linear independence, that is, if we have this vectors a1 bar, a2 bar, an bar, we say this set of vectors is linearly independent this is linearly independent if the linear if there is a linear combination x1 x2 a2 x1 a1 bar plus x2 a2 bar plus xn an bar equal to 0. This is possible if and only if all the x when all are identically equal to 0. That is what it means, essentially saying is that if there is a linear combination of A, that is there is that is essentially if there is that is if you that is any linear combination x1 a1 bar plus x2 a2 bar plus so on xn an bar, okay, this is equal to 0 only if each xi, that is x1 x equal to x2 equal to so on equal to xn equal to 0, and if if any of these coefficients, right, is non-zero, then the linear combination is not 0. All right. So, essentially it means that the only linear combination of this vectors a1 bar, a2 bar, an bar, that is 0, is when all the coefficients are identically equal to 0. All right. So, put the same thing in other words, it says that is there do not exist, okay, just understand this, there do not exist scalars x1 x2 xn not all 0 this is an important statement, not all 0, such that x1 a1 bar plus so on xn an bar equal to 0. That is, there do not exist any set of any scalars x1 x2 an not all 0 such that x1 a1 bar plus x2 a2 bar so on up to xn an bar equals 0. That is, the only time this is 0 is when all the scalars are 0, which means even if one or a few of them are non-zero, then the linear combination is not 0. Such a set of vectors is known as a linearly independent set of vectors. We call this as basically linearly independent. So, this is essentially known as your linearly, this is known as your linearly independent set of vectors. And for example, let us take a look at, let us take a simple example. Let us take 1 minus 1 1 then let us take this matrix A2 bar equal to 2 1. So, we have 1 minus 1 1, 2 1 1 minus 1 1 2 1 minus 3, and A3 bar equals 7 minus 1 minus 3, right. So, 7 minus 1 minus 3, 2 1 minus 3. Now, let us ask the question, are these set of vectors are A1 bar, A2 bar, A3 bar, we ask the question, are A1 bar, A2 bar, A3 bar, are these linearly independent? And we will show that they are not linearly independent. In fact, there exists a non-zero linear combination, there exists a linear combination with non-zero combining coefficients such that the linear combination equals 0. That is essentially how we are going to demonstrate that these are not linearly independent. For instance, if you look at 3A1 bar plus 2A2 bar, which is basically 3 times 1 minus 1 1 plus twice A2 bar 2 1 minus 3, then you can see this is equal to essentially 3 times 3 plus 4, that is 7, minus 3 plus 2, that is minus 1, 3 minus 6, that is minus 3, which is essentially nothing but which is equal to A3 bar. So, 3A1 bar plus 2A2 bar equal to A3 bar. So, you see the 3A1 bar plus 2A2 bar equal to A3 bar, which implies that 3A1 bar plus 2A2 bar minus A3 bar equal to 0. So, if you set x1 equal to 3, x2 equal to 2 and x3 equal to minus 1. So, x2 equal to 2, x1 equal to 3. So, we have x1. So, we have x1 A1 bar plus x2 A2 bar plus x3 A3 bar equal to 0, where not all are 0. In fact, you can see neither is 0, neither, in fact, you can say all are not 0 in this case. Okay. So, therefore, these are not linearly independent, alright. So, these are not linearly independent, we can say these are linearly. So, that says A1 bar, A2 bar, A3 bar, these are not linearly independent, and these are, therefore, you can say these are linearly dependent. On the other hand, if you take A1 bar, A2 bar, so on the other hand, if you take A1 bar, A2 bar, now you can show that these are linearly independent, right? These are linearly independent. Not very difficult to show that these are linearly independent. that is there do not exist there are no scalars x1 comma x2 not both 0 such that x1 a1 bar plus x2 a2 bar equal to 0. So, that is there do not exist scalars x1 x2 not both 0, right. So, that is at least one of them is non-zero such that x1 a1 bar plus x2 a2 bar equal to 0. Alright. Now, in fact, how do we systematically determine the rank, and this is via row and column elimination, and this is what we are going to come to. Alright. So, for a system, so in just a little bit, of course, we have not illustrated at this point a clear procedure to determine if the columns are linearly dependent or the columns are linearly independent. Previously we simply showed a linear combination of the column of the vectors which reduces to 0. In this case we are saying that there is no linear combination which is equal to 0 with at least one of the coefficients non-zero. So, how to systematically determine or determine linear dependence or linear independence, that is via row and column elimination, which we are going to see shortly. Okay. So, this brings us to the next important concept, which is essentially that of the rank, which is what we set out to discuss. So, now we come to the notion of the rank of a matrix. Now, rank of a matrix A this is equal to the maximum number of linearly independent columns, which is equal to the and this can be shown, we are not going to explicitly show this, that this maximum number of linear independent columns is also equal to the maximum number of linearly independent columns, which is equal to the maximum number of linearly independent rows. In fact, this is what we call as the column rank. This is basically what we call as the column rank, and this is what we call as more specifically the row rank, and we can show that for any matrix A, column rank equals row rank, column rank equals row rank, which is what we call as simply the rank of matrix A, and which is less than or equal to the minimum of the number of rows comma columns. Alright. So, this is rank has to be less than or equal to minimum of the number of rows or columns. So, therefore, it has to be less than both the number of rows as well as the number of columns. The maximum it can achieve is the minimum of the number of rows and columns, it cannot be greater than that. Alright. The rank of a matrix, any matrix A, the maximum value of that can be the minimum of the number of rows and columns. Alright. So, it is always less than or equal to the minimum of both the number of rows and the number of columns. And what is the rank? The rank is the minimum number, it is basically the maximum number of linearly independent columns or the maximum number of linearly independent rows. and both of these are actually the same, right. This is basically maximum number of linearly independent columns is the column rank, maximum number of linearly independent rows is the row rank, and actually it can be shown that both these quantities are the same, and this is what we are terming as the rank of the matrix A. Okay. All right. And how to find the rank? We now come to this concept of row operations. How to find the rank? How to determine rank? This is a very important concept. This is via the row operations. You can simply do column operations. To get what is known as the row. So, this is basically known as the Gaussian elimination procedure. So, this procedure is essentially known as Gaussian elimination. For instance, let us again go back to our matrix A, that let us take the 3 columns that we looked at before, let us put them in, let us look at our A bar, A1 bar, A2 bar, A3 bar that we previously looked at. Let us put them together as, this is the first column, minus 1, minus 1, 1, A1 bar, 2, 1, minus 3, 7, minus 1, minus 3. I hope I got that right. That is 1, minus 1, 1, 2, 1, minus 3, 7, minus 1, minus 3. So, these are your 3 columns. So, this essentially becomes your 3 cross 3 matrix. So, you know that the rank has to be less than or equal to minimum of number of rows comma number of columns, minimum of 3 comma 3, which in this case is essentially 3. So, the maximum rank equals 3. So, rank can be equal to 3, but cannot be more than that. Okay. Now, let us start with the row operations. Now, what we are going to do is we have A equals 1 minus 1 1, 2 1 minus 3, 7 minus 1 minus 3. The first operation that we are going to do, so we call this as the row 1, we call this as the row 2, we call this as the row 3. Then what we are going to do is to add row 2 by row 1 and replace this with row 2. All right. Essentially, what we are going to see is we have to make essentially make the leading entries of each row as 0. All right. So, essentially this gives me, right, what does this give me? So, you have 1 to 7. So, let us write it this way, R 2 is replaced by R 2 plus R 1. So, this is 1 plus minus 1 0, 2 plus 1 that is 3, 7 minus 1 that is 6, third row is as it is 1 minus 3 minus 3. Now, you replace R 2 by R 2 by 3, divide by 3. So, this becomes 1 2 7 0 1 2 1 minus 3 minus 3. Now, we are essentially going to replace. Now, this entry, leading entry is reduced to 0, right. Now, the next row we can target to reduce 2 of these entries to 0. So, we can do R 2 replaced by R 2 minus R 1, and that essentially means that you are going to have 1 2 7 0 1 2 0, I am sorry, R 2 R 3 replaced by R 3 minus R 1. R3 replaced by R3 minus R1. So, this will be 0 minus 3 minus 2 minus 5, this will be minus 10, and now we do R3 is replaced by R3 plus 5 times R2, which is essentially 1 2 7 0 1 2 0 0 0, and you can clearly see the entire third row becomes 0. So, the third row is completely 0, and therefore, you have 2 non-zero rows. Essentially, you have 2 non-zero rows. Implies the rank equal to 2. Okay. Or essentially, and we had seen this before, that in fact there are 3 columns, only 2 of them are linearly independent, right. So, maximum number of linearly independent columns, which will also be equal to maximum number of linearly independent rows, this is equal to 2, we had seen that. So, this implies essentially, as we had seen before, maximum number of linearly, let me write it clearly, maximum number of linearly independent which is equal to maximum number of is equal to maximum number of linearly independent rows. And in fact, these leading non-zero elements of each non-zero row, these have an interesting name, these are what are known as the pivots. So, these are leading non-zero elements of each row, these are known as pivots. So, you essentially have 2 pivots, you can also see it in terms of the pivots, right. So, you have 2 non-zero pivots, essentially the rank of this matrix is 2. Maximum number of linearly independent columns is 2, maximum number of linearly independent rows is 2, and when you do the row elimination, you can see that the number of non-zero rows is 2. Similarly, you can do column elimination also, although row elimination is what is usually preferred, and this is known as the row echelon form, the reduced row echelon form. This is known as the row echelon form of the matrix, which you get via Gaussian elimination with the pivots, alright. So, from the row echelon form, the number of non-zero pivots essentially gives you the rank of the matrix, which is a very important property, as we are going to see in the subsequent modules. Alright, so let us stop our discussion here. We will continue our discussion on matrices. In fact, as I told you, matrices form a very important component. In fact, linear algebra is sometimes also known as matrix algebra. So, our discussion of matrices and various types of matrices, the properties and the various manipulations, very useful, the various uses of these is going to form essentially the bulk of this course, alright. So, let us stop here and we will continue our discussion in the next module. Thank you very much.